Hey everyone, and welcome back to the channel. Today we are diving deep into something truly cutting edge. Running Meta's latest LLaMA 4 models locally using the power of K-transformers and Intel's advanced matrix extensions, also known as AMX. Now, LLaMA 4 represents a significant leap with its mixture of experts architecture as compared to its previous generations LLaMA 3, 3.3, 3.2, and 3.1, which were not mixture of expert models. LLaMA 4 Scout is a 17 billion active parameter model with 16 experts, totaling about 109 billion of parameters. Whereas LLaMA 4 Maverick is a much larger model, also with 17 billion active parameters, but a massive 128 experts, which is 400 billion total parameters. Running these locally is a challenge due to their massive size and complexity. However, it is becoming possible, and thanks to frameworks like K-transformers, which cleverly offload parts of the model to system RAM and utilize CPU accelerations that are inbuilt in Intel's AMX technology. Today, we'll be using the experimental support for LLaMA 4 in the support LLaMA 4 branch of K-transformers, which specifically adds support for these new meta models. Our goal today is to walk through the entire setup process and attempt to run both Scout and Maverick live on some seriously powerful hardware. We'll see how K-transformers and Intel's AMX handle these demanding models effectively and demonstrate the performance we can achieve and be upfront about any hurdles we encounter with this experimental setup. So stick around, you'll see the hardware, the software build, the configuration details, a live demo of working model, and a real-time performance breakdown. So let's get started. First things first, we need the models. So LLaMA 4 models, especially in the GGUF format, suitable for K-transformers, are quite large. Between the two of them, Scout is a more manageable model, but Maverick is enormous. Downloading these multi-gigabyte files directly can be tricky. So I'm using this Python script leveraging the Hugging Face Hub library, and it targets the GGUF version that we specifically need. So if you're used to LLaMA, you already know that Q4KM quantized models are the ones that are most popular, and they provide you with the best performance to size efficiency over here. So that's what we'll be using, Q4KM quantized models from the Unsloth's repositories on Hugging Face. This script can be easily adapted for either Scout or Maverick by changing the repo ID over here. We'll kick off the download for the LLaMA 4 Scout first, as this is the model we'll be demoing later. And the Q4KM version for the Scout is roughly around 65 gigabytes, so it will take some time to download. If you want Maverick, you just change the repo ID in the script, but be prepared for a much longer download time. The Maverick Q4KM is around 243 gigabytes. So while the Scout downloads, it's perfect time to talk about the beast of a machine that's making all of this possible. Let's dive into the hardware. Running these mixture of experts models locally, even quantized, demands a significant amount of resources, specifically system RAM. Here's the powerhouse setup that we have today. So, motherboard is the Asus Pro WSW790E Sage SE. This EEB workstation board is built for Xeon W3400 and 2400 CPUs, but it also secretly supports some of the Intel's experimental Intel's confidential, the QS and the ES CPUs, which is what we'll talk about in a little bit. This motherboard also supports up to massive 2 terabytes of DDR5 ECC RDIMMs across its 8 slots, and it is 1 DIMM per slot, which means you get a ton of memory bandwidth. Theoretically, with 4800 megahertz of RAM and 1 DIMM per slot, you get about 307 gigabytes per second of memory bandwidth. Yes, that's theoretical and we don't achieve that much, but that's the theoretical number that you can get with this. Now for CPU, we are using an Intel Xeon Platinum 8480 Plus. Well, not quite. This specific one is an Intel Confidential QIFS engineering sample. The retail 8480 Plus is a 56-core, 112-thread Sapphire Rapids beast with a base clock of 2 GHz and 105 megabytes of cache. But this one is 1.9 GHz, almost the same. Most importantly, it features Intel AMX. Both of them do. So the price difference of $10,000 for 8480 Plus retail versus $200 for engineering sample processor, it's a no-brainer for my experimental LLaMA 4 setup over here. All right, let's move on to memory. We need a lot of it. We have 512 gigabytes of DDR5 ECC registered RAM, 8 of 64 GB sticks. But why? So K-Transformers offloads expert parameters to system RAM. Scout Q4 needs about 65 gigabytes. Maverick Q4 needs a whopping 270 gigabytes just for the weights. This 512 gigabytes gives us plenty of headroom for either models and other OS processes as well. Let's talk about GPU now. While K-Transformers leverages CPU plus AMX heavily, a good GPU helps with attention layers. We have two NVIDIA RTX 4090s in this rig, and K-Transformers with Balance Serve primarily optimizes itself for a single GPU setup. We do have another GPU over here for some other AI operations that we would need in some future videos. So theoretically, you just need one 4090 or one GPU in your setup. For PSU, we have an EVGA 1600 watts power supply to keep everything well fed over here. Okay, let's focus on Intel AMX Advanced Matrix Extensions, what it is, and why is it a game changer over here. AMX is a hardware accelerator built into the cores of the newer Xeons like this 8480 Plus or QIFS. It's specifically designed to dramatically speed up matrix multiplications, which is the core math behind deep learning. It uses the special tile registers, so 8 1 kilobyte 2D registers and a tile matrix multiply, also known as TMUL, accelerator engine, to process matrix data. So it accelerates int8 or BF16s much faster than standard CPU instructions. And why is this critical for LLaMA 4 with K-Transformers? K-Transformers intelligently offloads the numerous computationally intensive expert layers of the mixture of expert model to the system RAM and CPU effectively. So, since these experts rely heavily on matrix math, having AMX means our Xeon CPU can process that workload significantly faster. K-Transformers keeps VRAM needs manageable. So Scout needs about 10 gigs of VRAM, Maverick about 12. By using system RAM for experts and AMX makes this the CPU tasks over here incredibly efficient at processing those experts. The GPU handles the attention layers, and this hybrid approach utilizes the whole system effectively for mixture of expert models. Okay, so our Scout download should be making good progress. Let's get K transformers set up. And remember, we need the specific support LLaMA 4 branch over here. First, clone the repo, check out the branch, and initialize the submodules. I'm going to use this local path over here. I normally create a dev AI folder in my home directory. Now, next, we need a dedicated Conda environment to keep everything separated out. So we'll be creating an environment, then activating it, installing some of the dependencies using Conda Forge, and then just validating whether everything is installed correctly. Now we'll be installing some of the packages that are needed for building. So we need libssl dev, libcurl14, openssl dev, and then some other packages that I'll be putting in my GitHub repo over here for ease of use. After you're done installing the build dependencies, then we'll be ensuring that we have the correct version of Torch, Torch Vision, and some other dependencies installed in the environment. And we'll make sure that Torch is correctly configured before we move forward over here. All right, with the environment ready, let's build K transformers. And this is going to take some time. So we must set use balance serve as 1, as LLaMA 4 support on this branch only works with this backend. Now export the variable and run the install script. This will compile the custom C++ CUDA kernels for you. This build definitely takes a while, maybe about 20 minutes. So let's talk K transformers and balance serve meanwhile. K transformers works by module injection. It replaces standard PyTorch model parts with its own optimized versions using YAML config files. These optimizations can include quantization, custom CPU kernels, which leverage AMX, and GPU kernels. The balance serve backend, introduced around version 0.2.4, is designed for multi-user concurrency. And some of the key features of the balance serve backend is continuous batching, which dynamically groups requests for better hardware utilization, chunked prefill, which breaks down long prompts for efficiency, asynchronous C++ scheduler for low overhead request handling, and efficient GPU sharing, which improves overall throughput with multiple users. And benchmarks have showed around 130% throughput gains with 4 users over here. So why is balance serve essential for LLaMA 4 plus AMX? It's built for its hybrid workload. It manages the data flow, sending attention and non-expert layers to GPU, while coordinating the CPU using AMX to process the relevant expert layers stored in RAM. Its concurrency helps keep both CPU's AMX units and the GPU busy. maximizing our hardware use and bypassing VRAM limits by leveraging the system RAM and the AMX accelerated CPU, which is huge. Now, if your build has failed, let's take a look at that. If let's say, so in my case, the build has passed successfully, so we are okay over here. But in case your build has failed, you'll have to check the dependencies meticulously, correct some CUDA, PyTorch mismatches, correct your G++, make sure it is greater than version 11, CMake is greater than version 3.25, and etc. I cannot comment on what exact issue you will face, but there is a possibility. I've seen in the forums a lot of users face a lot of different issues, but if you follow the instructions correctly on their GitHub repo, more often than not, it works. All right, K-Transformers is built now, and our LLaMA 4 Scout GGUF download is also complete. Maverick would take much longer, but the setup process for both is identical. For Scout Q4KM, you should have GGUF files totaling around 65 GB inside a folder named Q4KM, which is created by the download script already. I've organized my models under my folder, which you will see /media, mukul, extra, models, unsloth, with separate directories for LLaMA 4 Scout 17B, instruct, and LLaMA 4 Maverick 17B instruct. The GGUF files reside within Q4KM subfolder inside each of these folders. Now, this is absolutely critical. Just having the GGUF files isn't enough for this K-Transformers branch. We need 4 additional configuration files and tokenizer files for each model. These files define the model's architecture and text processing. We need to get them from 2 places, and importantly, use a custom config.json. First, the custom config.json is available in K-Transformers support LLaMA 4 branch, and it requires a specific version of this file for LLaMA 4 models. You cannot use the standard one from Hugging Face. Download this exact config.json from the K-Transformers documentation, and then you have to download the tokenizer files. So tokenizer.model, tokenizer_config.json, special tokens map.json, and these you can get from the Hugging Face metas repo. Now, when you find these 3 tokenizer files on model's Hugging Face page under files and versions, you will have to put them in a particular directory, and let's organize that. K-Transformers needs the GGUF files in one directory, for example, in your Q4KM subfolder, and the 4 config tokenizer files in, let's say, a parent directory that you can specify as -- model path over here. In case of Maverick, you will move on to LLaMA 4 Maverick folder as the parent directory and keep your 4 files over there. So the same config.json and the same tokenizer and the tokenizer files for Maverick in that parent directory, and your GGUF file in the Q4KM directory. All right, the moment of truth. K-Transformers is built, model is downloaded, configs meticulously placed. Let's try launching the inference server and start with LLaMA 4 Scout, which we expect that it should work because all the documentation around in the K-Transformers forums talks about the Scout model. So here's the command to launch the K-Transformers server for LLaMA 4 Scout. And note that I'm using CUDA visible devices equals 1. so that I can use my second GPU for this particular model over here. If I do not specify that, then the model will be using the first GPU, which is also connected to my monitor, and I do not want that. Okay. In this particular command, you'll also see that I'm setting up certain attributes over here. Some of these arguments are, of course, CUDA visible devices is one, which is targeting a specific GPU, which is the second GPU. This part is optional. You can ignore that if you don't want. Then there is a Python command which specifies path to ktransformers server script, which in my local is in the directory home mukul dev ai ktransformers. I'm also specifying the port 10002, which is the API server port. The model path over here is the path to the Scout directory containing the custom config.json and the tokenizer files. The GGUF path is the path to the Scout subdirectory containing the actual GGUF files. So all the way till Q4KM. Now, optimize config path. This is the path to LLaMA 4 optimization rules provided by ktransformers. So this same file works for both Scout and Maverick. Now, max new tokens is 2048, which is the max generation length for Scout we have specified. KV cache size, which is the cache length, is 32K. The chunk size is 256, which is the processing chunk size for balance serve over here. Max batch size of 4 means that the max concurrent request for balance serve is 4. And the backend type, like we talked about earlier, balance serve, which is mandatory backend for LLaMA 4 support. And you have to wait for a little while after you hit enter. After some time, it is a success. You can see it loading the config, the GGUF weights, detecting the 16 export for Scouts, initializing the balance serve backend, and now it is listening on port 10002. Excellent. LLaMA 4 Scout is running locally. Okay, with our Scout server running, let's connect a user interface. And we'll use OpenWebUI, which is a popular open source frontend that can talk to OpenAI compatible APIs, which ktransformers provides. So assuming you have OpenWebUI installed, and Docker is the easiest option. If you do not know how to install it, I have a separate video for setting up OpenWebUI in your local with LLaMA, but you can very easily switch over and configure this OpenWebUI for ktransformers. And let me quickly show you how you can do that. So open it in your browser at localhost 3000. Go to OpenWebUI settings, so admin settings, connections, and then you will have to change your connection to localhost 10,002/v1 over here, which is the chat completions endpoint right here. So this is an OpenAI compatible API, which is why this works for us. Okay, let's go back to the main chat screen and select our new Scout model from the model dropdown. And this is the time to chat with LLaMA 4 Scout. Okay, let me put this prompt over here. Okay. And let's see if it can create a Python snippet to list all the files in the current directory. And it is generating the code over here. Pretty cool. All right. Okay. What are the main benefits of using Intel AMX for AI inference? Let's see if it can answer that, right? Okay, so response coming through mentioning, let's see how we feel about this response. I'll leave this response over here and let me see in your comments if you made it through up until this point in the video and how do you feel about this particular response from Llama 4. Okay, so this is fantastic. Running a 16 expert Llama 4 model locally with this kind of responsiveness is a huge step forward. Okay, let's peek under the hood while Scout is working. We'll use htop for CPU RAM and nvidia-smi for GPU stats. You can see in htop that as soon as we start an inference process, all these cores go crazy. And this is exactly what we want. You can also see the RAM cached, the KV RAM over here, KV cache over here, cached in the RAM. And this is also consuming a significant amount of RAM for us. And you can see every time when we hit inference, you can watch the CPU cores light up during the generation. And that's the gate transformers using Xeon cores accelerated by AMX to process those expert layers. Now, NVIDIA SMI, and if we do the watch on it, we are watching GPU 1 specifically over here. Remember, we specified CUDA visible devices as 1 and see the GPU spike as it handles the attention. And you can see that the GPU spike is not as big as the CPU spike, showing how much CPU is doing the number crunching for us over here as compared to the GPU. While Scout runs, there appears to be a bug or some kind of incompatibility specifically when loading the larger Maverick model's GGUF weights. And this isn't entirely unexpected when we are working with cutting edge models on development branches, but it's important to see it firsthand over here in case you guys are struggling too. If you are able to load it by using some hack, I'd be interested to see that. Please share that in the comment section over here. All right, so this is editor Mukul from Future, and while I was recording this video and editing it, I took a look back at K-Transformers repository, and they have actually now apparently fixed the issue with the Llama 4 Maverick. So what I'm going to do is leave the rest of the video assuming that Maverick is not working because I haven't tried that out. But right after this video, I'll start working on the Maverick video, and that will be the small video dedicated only on Maverick. And we'll find out if the Maverick is indeed fixed in the newer branch that they have come out with. But yep, stay tuned for that one also. Okay, so based on our testing today, with this experimental support Llama 4 branch, there are some current limitations. And there are some future roadmaps that K-Transformers team has pointed out. So, number one, balance serve backend is the only backend that is supported at this point of time. Llama 4 support is tied to this particular backend. And second, the experimental branch status hasn't been removed yet. It is not yet merged to the main branch. Potential for bugs are high on this branch. It also requires newer dependencies like Transformers 4510. And no multimodal support is available currently. So this setup is text only despite Llama 4's native multimodal capabilities. So they do have a future roadmap. calling out that it will eventually be merged with the main branch. The goal is to merge the LLaMA 4 support into the main branch of K-transformers, of course, after stabilization though. So hopefully this will include the fix for the Maverick loading issue. If you found this tutorial and transparent look at the process helpful, please hit that like button. It really helps the channel. And make sure you are subscribed and have the notification bell on for more explorations into local AI, hardware, and software. All the crucial links, K-Transformers GitHub, the Hugging Face model repos, the Python script, hardware details, OpenWebUI are down in the video description. Let me know in the comments, have you tried K-Transformers yet? And are you planning to try it with LLaMA 4? Did you get Scout running? Did you encounter the same Maverick issue or find a workaround? Share your experiences. I'll be more than happy to respond back in the comment section below. And thank you so much for joining me today. Keep experimenting, keep learning, and I'll see you guys in the next video.